It is 12:45.
That's impressive. Okay, so good luck and take it away.
Yeah, so greetings to all according to your time zones. So I would like to thank the organizing committee for giving me this opportunity to present our work. So the title of the talk is Shadows and Negative Precession in the Non-Kerr Spacetime. The outline will be accordingly. So April 10, 2019, ngEHT released an image of an ultra-compact object. So the reason for highlighting that particular term is its true nature is still a mystery. So now, because a lot of recent research works suggest other eligible candidates, and now these eligible candidates have unique effects on their surroundings, like the fingerprints. So now we receive this information in terms of either gravitational waves or orbital precession of the bodies or the stars, or gravitational lensing, which forms the basis of the shadow formation. So in our work, we have studied the time-like geodesics and shadow formation for a deformed Kerr spacetime to answer the following questions. So after applying Janice-Newman algorithm to the deformed Schwarzschild metric, we have got this particular metric, that is a deformed Kerr metric. The parameters are defined in this region, and this is what makes it different from the original Kerr metric. This h of r theta is the deformation function. The epsilon is the deformation parameter. Now, if we see closely, then we will see when you set epsilon to 0, this above metric reduces to the original Kerr metric. And now this deformation parameter is bound by an upper limit of less than or equal to 19. These plots over here are of the event horizon for different deformation parameters and spin parameters. So if you see this particular third plot, you will see a variant of the deformed Kerr spacetime. So when the epsilon is -1 and the spin parameter is 0.8, we see a discontinuity in the event horizon in the equatorial plane, which exposes the central singularity to the environment and which suggests the formation of a deformed Kerr naked singularity. So the condition for which we observe the formation of a directional naked singularity, for which spin parameter has to be between 0 and 1, is that the epsilon has to be greater than 0. So that is the condition for formation of deformed Kerr naked singularity. In order to study the precession, this equation over here is a very well-known equation of orbit in the Newtonian case, where this k is the eccentricity. The p and small m here denotes are some positive constants which are going to help us understand what type of precession we are going to observe. We have considered small eccentricity approximation where the higher order eccentricities have been ignored. So the first image, we use this solution to solve the differential equation of orbit which we received from the metric, which we derived from the metric, and then we use, by solving that, we get the values for p and m, where if m is less than 1 will suggest a positive precession, and if it is greater than 1, which would suggest negative precession. So this particular image over here is to explain what positive precession actually means. So the angular separation after successive approaches to the perihelion, this brown ring over here is the perihelion approach. So if the particle reaches the perihelion point after 2 pi rotation, it would suggest positive precession, while if it reaches in this second figure before 2 pi rotation, would suggest negative precession of the orbit. In simple terms, if I tell is that if the orbit precesses along the direction of the particle's motion, if the orbit precesses along the direction, that will be considered as positive precession, and if it is precessing against in the opposite direction of the particle motion, it will be considered as negative precession. So yeah, actually there is some disturbance over here.
Mina, Paul, are you able to turn off the mics of people who are not speaking?
Yeah, just did.
Okay, thank you.
Thank you. Yeah. So the shadow, the formation of shadow, the basic idea behind shadow is gravitational lensing phenomena, where the light is bent due to when it is in the vicinity of ultra compact object. So the detailed concept would be discussed in tomorrow's lecture by Dr. Dipanjan De. But for now, I'm going to give you a brief idea. So for shadow to form, photon sphere plays a vital role. And here you can see the condition for the existence of the photon sphere. Then the next important part is the impact parameters, which we will be using to find the expression for the celestial coordinates. So this image over here will make us understand what is the importance of this alpha and beta in order to get the shape of the shadow. Moreover, we have defined the amount of deformation as the difference between the alpha of the deformed Kerr spacetime and the alpha of the normal Kerr spacetime. And the measurement of this amount of deformation D has to be done along the particularly this axis, beta is equals to 0 axis. So the results which we received, these plots over here would tell us the information about what kind of precision you will observe for different variants of deformed Kerr spacetime. So if you consider the spin parameter to be 0, that is a deformed Schwarzschild spacetime, we observe that the value of m exceeds 1, that is for negative precision, only when the epsilon, the deformation parameter, exceeds 20. But since the deformation parameter is bound by an upper limit, so we infer that the negative precision is not allowed in deformed Schwarzschild spacetime. The next image over here is for the spin parameter to be 0.7, where we observe the negative precision for around epsilon is equals to 14. Now, as we go on increasing the spin parameter, we observe negative precision at relatively smaller values of deformation. This particular plot over here, in this, the blue shaded region is the region for the existence of a deformed Kerr naked singularity, that is for epsilon to be greater than 1 and the spin parameter to be between 0 and 1 greater than. And this dotted line over here separates the positive precision from the negative precision. So all the red dots which you see in this figure are the solutions for the negative precision. Yeah, so these are the plots for the shape of the shadow. The solid dotted line which you see on your screen is for the normal Kerr spacetime, the shape of the shadow in normal Kerr spacetime. Now, since we have introduced the deformation, this is the case for deformed Kerr black hole, where the epsilon is negative of 1, and we observe a oblate shaped shadow. The amount of the oblate shape increases as the spin parameter increases. You see a convex bulge over here, which separates it from the normal Kerr metric. The amount of deformation D here has a negative value. And for the case of deformed Kerr naked singularity, instead of a convex bulge, we observe a concave bulge or a prolate shape, where this particular is for epsilon is equals to 1 and A is equals to 0.8. And here we have considered a higher values of deformation, where you can see the amount of deformation is huge, is effectively visible. Now, a lot of research, a lot of literature suggests that simultaneous occurrence of negative precision and shadow is not allowed. But this is one of the examples which suggests simultaneous occurrence of negative precision as well as shadow formation for these particular parameters defined over here. So any evidence, like for example, the Schwarzschild and the normal Kerr metric, they don't exhibit negative precision. So any evidence of simultaneous occurrence of negative precision and the shadow formation would discard the possibility of the Schwarzschild black hole or Kerr black hole at the center of our galaxy. It will increase the probability of existence of deformed Kerr naked singularity at the center. So the entire talk has the conclusions. I have already mentioned all these conclusions. So this is a brief slide for the entire presentation. And this would be the references. I would like to thank the collaborators for this work, and thank you for your patience and questions and comments. I would appreciate questions.
Thank you, Aadarsh. Are there questions? I see Aditya have a question.
Yeah, so I have a two-part question. You can answer either or like both of them. So the first question is regarding the metric that you chose. So how exactly do you know that this is a deformed Kerr metric? By that, I mean, for example, certain compact objects that deviate from Kerr also have something called a tidal deformation signature, which means that it would not be a Kerr metric, it would indeed be a rotating neutron star. So on the basis of your metric, how does it know that it's a deformation of the Kerr metric, and how does it differ from, let's say, a rotating neutron star? And very briefly, the second question was, you mentioned the photon sphere of the singularity. So does this photon sphere have a similar structure like, you know, the Kerr photon shell that was done by the EHT scientists, in which there was a subring structure attached to it and it was governed by 3 parameters and so on and so forth? So how does the photon sphere of this singularity differ from the Kerr photon sphere shell rather?
Yeah, okay. So I'll go back to this. Thank you for the question. I'll be answering your first question of the metric. So here we have used this Janice-Newman. So initially, whenever you use Janice-Newman algorithm, there is a seed metric, and then you transform that seed metric into a rotating version of itself. For the particular assumptions you have to consider, it should be asymptotically flat. It should be, so there are particular assumptions I will be stating. So we have considered the seed metric to be a deformed Schwarzschild spacetime. And after applying the Janice-Newman algorithm, we have received this particular metric. Now, if you consider the deformation parameter to be 0, this will reduce to a original Kerr metric. So one of the way of deriving the Kerr metric, the normal Kerr metric, is applying Janice-Newman algorithm to the Schwarzschild spacetime. So similar process has been done here. Instead, we have already introduced the deformation in the Schwarzschild spacetime. So that is how we have considered that this particular metric is eligible for a deformed Kerr metric. So was this answered?
Yeah, I'll get back to that if the host allow me to ask a follow-up question, if that's okay.
For the sake of time, if you could continue in the chat,
sure. No
that
problem.
would be great,
Okay.
because you know, just because of the schedule. So
No
thanks again, and I will do this honor of clapping to people. Bravo. And new information is that I will be showing, or I will make a new note, because it's I cannot work. This is supposed to say 2 minutes. I will be showing that, so I'll just look at me for the speakers to be aware of time. Okay, and I'd like to invite.
Just hello. For
yes?
that second answer, I would just like to show the statement that this particular value of R does not vary, is not dependent on the deformation parameter. So there would be sufficient difference in the radial part of the photon sphere, but you will observe some difference in the angular part of the photon sphere. But we will I will discuss with him in the chat. Thank you.
Okay, thank you. So I'd like to invite Joshi to give the second talk at our session. Aadarsh, may, oh, you did stop sharing your screen. Joshi, are you there?
Yeah.
Are you able to share your screen? So, okay, I think it's going to work.
Yeah. Okay.
So, so we still see your folder.
Hello. Can you see my slide?
No, we only see the folder.
Oh.
maybe retry, or maybe, you know, when you're sharing share screen and not application.
Yeah, that looks like the whole desktop there.
Well, let's try again. Oh, great. So, Ashok, just tell us what time zone you're in, because we're all very curious, and it looks like it could be an exciting middle of the night for you. And you need to unmute yourself.
Oh, sorry. Actually, Aadarsh and me are in the same lab. So the actually Indian Standard Time around 1 o'clock. Okay.
Okay, but we have lost your presentation now. So we only see, we can, okay.
Okay.
Well, let's give it a second. Yes, we see the presentation. If you could go to the slideshow mode.
Yeah.
We only see the first slide now, and we see the window. And we do see your cursor. Can you press the slideshow button?
Okay.
Yeah, I think it's gonna be fine now.
Okay. Can I start?
Please do.
Okay. Okay, thank you. First of all, I would like to thanks to the organizer to given me opportunity to speak here. In this talk, I will tell you about a brief conclusion and a result from this paper, Shadow of a Naked Singularity Without Photon Sphere. So in this paper, we show that shadow of a null singularity also be possible without photon sphere. Okay. In general theory of relativity, importance of a shadow of a compact object in the regions of a strong gravity can reveal the structure of spacetime, which is important to study the compact object in the galactic center. Universe is full of possibility, so there are maybe other compact object also be possible, like strong time-like and null-like singularities. So for experimental purpose, it is interesting to take all possible outcome. We can match and test it. In gravitational collapse, a spherically symmetric homogeneous dust collapse always terminate into a black hole. But depending upon the initial condition, the final spacetime can be a black hole or naked singularity. So one of the best example is given in this paper, equilibrium configuration from gravitational collapse. It is shown that JMN spacetime with a central time-like singularity are obtained as an asymptotical equilibrium state of the quasi-static gravitational collapse. So in this diagram, we show the Penrose diagram of the black hole, null singularities, and time-like singularity. Here I will briefly introduce about the Schwarzschild, null, and JMN spacetime, Joshi, Malafarina, Narayan spacetime. These spacetime are static, spherically symmetric, and which have a space-like, null, and time-like singularities. In Schwarzschild spacetime, singularity is hidden within the event horizon and have a space-like singularity. And in this null spacetime, ds square null, okay, in this spacetime, develop a strong null singularity at the center. So I called it as a null singularity spacetime. Actually, this spacetime resemble with a Schwarzschild spacetime at a large distance. Okay, so I'm not actually expert in the causal structure, but I think this particular null singularity spacetime, which is mentioned here, is a marginal case. Okay, here we can see that in this past null infinity. So we can say that the light rays which emanate from the singularity is infinitely redshifted. Therefore, asymptotical observer will not able to see the exact singular point. So I think this is the very interesting feature in this null singularity spacetime. And in this Joshi-Malafarina-Narayan spacetime, in this paper, equilibrium configuration from the gravitational collapse. Okay, in this paper, it is shown that in asymptotically time, J-main spacetime can be formed as an end state of the gravitational collapse of the matter cloud with zero radial pressure and non-zero tangential pressure. This spacetime has a time-like singularity at the center, and J-main spacetime match with the external Schwarzschild spacetime at R is equal to RB. The full study of this spacetime is given in this paper. Okay, and the line element of this J-main spacetime is this, and where the ADM mass of this spacetime is equal to the half of the m naught RB. Here m naught RB is the positive constant. Okay. So in this figure, in the first column, we show the nature of the effective potential of the null geodesic in J-main, Schwarzschild, and null singularity spacetime. In the second column, we show the light trajectory in this spacetime. In this, we show that the trajectory of the photon, which are coming from the far away source and deflected due to the curvature, and this geometrical deflection caused the shadow of the spacetime. Here, black line represent the critical light ray having the impact parameter B is equal to B critical, and the value of the B critical in the Schwarzschild and J-main spacetime are same, 3√3m. But for the null singularity, it is only m. So in this shadow simulation, third and fourth column, we take a simple model. So we consider the spherically symmetric, radially freely falling thin Christian matter, which radiate a monochromatic radiation. In the third column, we showed how intensity vary with the impact parameter B in the Schwarzschild, J-main, and the null singularity spacetime. And in the fourth column, we show the shadow simulation for the J-main, Schwarzschild, and null singularity. So we can clearly see that in J-main and Schwarzschild spacetime shadow size is same. So it is very difficult to distinguish this spacetime. But in the null singularity spacetime, this is almost around 5 times smaller than the Schwarzschild shadow. Okay. So in this table, the angular positions of the Einstein ring here theta e, okay, and the few relativistic Einstein ring theta n are shown for both cases, the Schwarzschild and null singularity spacetime, and also shown the separation between the two conjugative ring. In this table, all the numerical calculation is for the Sagittarius A star. Actually, it may be we see the relativistic subrings, but not exactly the photon sphere. In this table, we see the similar types of a subring also be possible in null-like naked singularity spacetime. The n is equal to infinity here. Case represent the innermost critical ring, which form the edges of the shadow region, and its angular position is denoted by theta infinity. Okay, here. And this ring is produced by the critical ray having the impact parameter B is equal to B critical, and for null-like it is M, and for Schwarzschild case it is a 3√3M. Here we can see that 28 and 5.4. Okay, so this photon ring theta infinity shows the edge of the shadow, and so this types of a photon ring also be possible in the null and time-like naked singularity. Okay, conclusive remarks. In the null singularity spacetime, there is no need of a photon sphere for formations of a shadow. Shadow can be cast by a singularity itself, which can be a time-like or a null-like singularity. The angular positions of Einstein ring for the both the Schwarzschild black hole and the null singularity are found to be almost equal. This signifies that in weak field limit, the null singularity spacetime behave like the Schwarzschild one. The important characteristic of the null singularity is that shadow of the singularity would be a considerably smaller in size as compared to the shadow of a black hole. Near the null singularity, the quantum gravity effect should be a dominant, and therefore such a quantum gravity effect might be manifested or can be observed in the shadow cast by the null singularity. And the relativistic rings are well separated, and so many of them can be easily resolved as compared to the Schwarzschild case. So these are the main points which may be helpful to understand the central strong region, central strong field region. In this table, we take mass M is equal to 4.3 into 10⁶ solar mass for Sagittarius A star. So we clearly see that the shadow of the Gemin and Schwarzschild spacetime are the same, 56 micro arc second. But for the null singularity spacetime, it is almost 5 times smaller than that, around 10 micro arc second. Okay, so thank you. If you have any question, please.
So unfortunately, we are a little behind because of these technical problems. So let's keep the questions to the chat and to the preferably to the Slack channel. I think this is interesting to discuss, in particular, given that ngEHT made this remark in the ngEHT papers about naked singularity shadows being significantly smaller than the black hole shadow. So I think it's interesting to discuss. This is kind of against that argument, the numbers that you are showing. Okay, so I would like to, first let me thank you. Bravo.
Thank you.
I would like to ask Chen to share the slides. If thanks for stopping. Okay, wonderful. And I will ask this usual question instead of the institute, because you are showing your institute here on the slide. What's the time zone you're in?
Yeah, thank you. I'm Chen from Institute of Physics, Academia Sinica from Taiwan. So this is Taiwan local time. It is almost 4 o'clock a.m.
So you are, congratulations, you are the winner today, I think.
Yeah, I'm supposed to be the most impressive one.
In this category of how late one can give a talk. Okay, so take it away, please.
Okay, thank you. So the presentation of the talk I'll give today is essentially based on the one of my recent paper, which was published in JCAP last year, as you can see here. Oops. Okay, so today I'm going to talk about the possibilities of testing one interesting features of black hole beyond Einstein gravity by using black hole shadows. So such a feature is essentially the Z2 asymmetry of the black hole spacetime. So by definition, if the black hole solution has no Z2 symmetry, then its northern hemisphere and the southern hemisphere will look different. And such an asymmetry would usually appears when you consider for example, for the underlying theory containing some parity violating interactions. For example, if you consider some effective field theory of quantum gravity by including the couplings of projection scalar here and coupled with some other higher order curvatures interactions, or coupled to other dynamical scalar field, then the rotating black hole solution of this theory would naturally lose their Z2 symmetry. And such a violation of Z2 symmetry is usually induced by the spin of the black hole because of its close relation to the projection scalar, as I mentioned above. But the point is that usually the black hole solution, rotating black hole solution of this theory are very complicated. And the motivation of my work is to construct a parameterized Kerr-like metric and focusing on the Z2 asymmetry of the space-time, and to see whether we can use black hole shadow to say something, to put some constraints on this violation of Z2 symmetry. Okay. So in addition to construct the solution without Z2 symmetry, I want to also preserve the existence of color-like constant in the space-time. And this is essentially associated with a very important symmetry of the Killing tensor. And this also implies that the geodesic equations of this space-time are completely separable. And this means that we can start with a very general metric proposed recently by Papadopoulos and Kokodas in 2018. So this became metric in the Boyer linguist coordinates. The metric function contains 5 arbitrary functions of R and 5 arbitrary functions of polar angle Y, which is cosine theta here. And it has been proven that this PK metric, for this PK metric, the geodesic equations are completely separable. Okay. And as I said, in this work, I want to just focus on the violation of Z2 symmetry. So I would just change the parametric functions B. So this means that I will simply fix all the radial metric function A to be simply given by the Kerr expressions. But for the parametric functions, I will put some arbitrary function, small deviation function epsilon on top of their Kerr expressions, as you can see here. So of course, if we put epsilon I equal, all of epsilon equal to 0, then of course we get a Kerr metric. And furthermore, if we require that the Kerr metric to be asymptotically flat, it turns out that only epsilon 1 and epsilon 5 are theoretically relevant, and other deviation functions, epsilon 2, 3, 4, have to be 0. Okay. So this slide is just to convince you that by adding this epsilon 1 or epsilon 5 and changing them, we can, the Kerr-like space-time here is indeed Z2 asymmetric. So you can see from this curvature invariance, the behavior of the curvature invariance will be different in the North Hemisphere and the Southern Hemispheres, okay? So now the question is whether, how does shadow look like for this particularly interesting space-time? So to investigate the celestial coordinates, we follow the standard procedure. We define the celestial coordinates, alpha and beta, in the sense that this alpha beta plane is essentially the plane on which the shadow image is mapped. And we can have the equations for these alpha beta coordinates, as you can see here, and we simply call them shadow equations. And the point is that you can see that only epsilon 5 appears in the shadow equation. So this means that the shadow contour of the photon sphere or the photon region is completely blind to epsilon 1. And this is one important remark. And the other remark is that the shadow contour is symmetric with respect to the horizontal axis, as you can see from this plus and minus sign, this beta expression. And this is true no matter what the inclination angle of the observer is. So you may think that this is somewhat counterintuitive, because the black hole solutions that we are considering here is not Z2 symmetric, but its shadow image, the impact parameter of the photon sphere, is always symmetric with respect to the horizontal axis. Okay, so this is another important feature of this kind of solution. So let's put one more assumptions on the model. So basically, for example, if we require that the solution satisfy the solar system constraints, we can essentially reduce the degrees of freedom to 1. So the original 2, epsilon 1, epsilon 5, we can fix one of them to be the opposite of the other one. And we can also require that the Z2 asymmetry is induced by the black hole spin, as we mentioned from the effective field theory argument. So the simplest choice of this function epsilon tilde is essentially, we can simply assume it to be proportional to the spin of the black hole, and it is also a linear function of the cosine theta. Okay, so this is the shadow image. So as you can see, if we change the value of this deviation parameter epsilon, we find that we only change the apparent size of the shadow. Okay, it doesn't change significantly the amount of distortion in shape. So basically, the amount of distortion is still determined by the spin of the black hole and the inclination angle of the observer, as what we have in the Kerr spacetime. Okay, so let's see what the image of M87 star would tell us about the constraints on this model. So according to the image, we know that the non-circularity is very small. The delta C is smaller than 0.1. And the apparent size, the angular diameter, is consistent with the Kerr result within 17%. Okay, so whether we can use this constraint to test our theory. So if you look at the figure on the left, so this shows the profile of the non-circularity in the parameter space. So if we fix the inclination angle to be 17 degrees following this purple line, we find that the non-circularity is always very small in this parameter space, irrespective of the value of epsilon. So it is very, very challenging to constrain epsilon using non-circularity of the M87 star. Okay. And if we look at the apparent size of the radius, we find that it is indeed possible to have some constraints on this epsilon. So this, I want to point out that this epsilon has no degeneracy with the spin. So this means that we can have a better constraint on epsilon if we can have an accurate measurement of the shadow image size. So this is very important. We know that the spin measurement is always very difficult. So this is a conclusion. So in this model, we propose a class of Kerr-like metric which violates Z2 asymmetry, has no Z2 symmetry, and it has a color constant and the separation of Joles equations. And we find that the shadow contours is always symmetric with respect to the horizontal axis, regardless of the inclination angle. And the point is that the deviation parameter epsilon can be tested using the current apparent size image. For example, if we have a better image from the Sagittarius star in which we know better the mass and know better the distance, so then we can have a better constraint on this epsilon. So that's it. Thank you.
Thank you very much. So unfortunately, we're still trying to catch up on time after this little lag we experienced. So I'll just invite the next speaker, but first let me clap. And let me invite you to discuss in a Slack channel, which I see there is some activity happening there at the moment. So I'd like to ask Sourabh Nampalliwar to give the next talk. And again, I would like to ask you about your time zone.
I'm in the same time zone as you, so almost
so not too
9
bad,
PM.
not too bad in comparison.
Yes,
okay,
yeah,
take it
yeah,
away.
Cool. So thanks a lot. Hey, everyone. My name is Sourabh, and I will talk about our recent results on testing GR with a theory-independent approach using black hole shadows. This is part of a work with my student, whose name is also Sourabh. So let me begin with a roadmap. So the first step is to start with a modification of GR. The modification can be at the level of the Lagrangian, which leads to a modified theory of gravity, or it can be at the level of the metric, which can lead to a non-GR metric. Both can represent violation of GR. They are different in spirit, let's say. The next step, once we have modification, is to calculate observables. So, for example, if we were using gravitational waves, then we would probably calculate the waveform or the phase of the gravitational wave. And depending on the observable, the modification may or may not be testable. Next step is to compare the model you have with data and use that to estimate the potential violations of GR. More precisely, we put bounds on potential violations of GR. So this is one example of a modified solution of GR. It's a non-Kerr metric. And a lot can be said about the metric. Many of you may have already seen it. Let me just mention two features of this non-Kerr solution. One is that it is axisymmetric, so it maintains the axisymmetry of the Kerr solution, but it breaks the Carter symmetry, so it does not have a Carter constant. For this talk, I would focus on two of the functions in the metric, A and W, which I have colored here in magenta. I will look at the leading order strong gravity parameter. I mean, the function is a bit involved, but I would only like to emphasize that we are going to look at W01, which is associated with W, and A01, which is associated with capital A. The most important thing to keep in mind here is that A01 affects the TT and the RR component of the metric, and W01 affects the TT and the T phi component of the metric. So this is the modification of GR we are going to explore. The next step is to, of course, calculate shadows. We heard a lot about this already, and this is a standard thing, so I'm not going to spend too much time here. I'll be happy to talk about it at the end. Let's come to data. So as I said, the focus of this talk is on shadows, but see Sourabh's talk on Thursday for talk. Now, EHT measured two quantities which are directly relevant for shadows. One of them is the size, which is the average of the shadow diameter measured over different orientations. And the other is the shape, which is, to be precise, which is the measurement reported is the standard deviation in the shadow diameter measured along different orientations divided by the average diameter. So there is the current, what I would call the current data, which is the estimates that EHT has reported using M87. So the size of the shadow measured with a 17% precision, and the shape, which is measured, which is the sigma of the shape is 0.05. And then I will, look into the future, what is potentially possible with next generation EHT. So a size measurement of the order of 5% precision and a shape measurement of 0.01. We'll make all our, let's say, observations at an inclination of pi/2, where all the effects in the shape and size are enhanced. So let me show you some results. This is the constraint on A01 parameter using current data. So A01 equals 0 is exactly GR, so no violation of GR, and that is recovered quite large. So the bounds are between -0.6 and 1.8. With future data, the bounds improve quite significantly, and we have For A01, bounds are between minus 0.6 and 0.5. Similarly, for W01, the current data gives a bound. I don't know why this looks a bit strange. Okay, yeah. So with current data, the bounds on W01 are something like minus 0.5 to 0.6. And with future data, the bounds improve again quite significantly, and we have the W01 bound plus 0.3. Now, where do these numbers, how do these numbers compare with what has been measured with other techniques? Because these parameters have been, the bounds have been provided for these parameters with other techniques. So for example, A01 has been constrained to the order of 0.1 with gravitational waves and to the order of 0.3 with X-rays. And what this shows is that with current data and even with future data, we don't expect this A01 parameter to be measured any better than what has been done with other techniques. For W01, the current data is not so good. Future data, we may get comparable estimates, but remember that this future data is expected to be around maybe after 10 years, and certainly the bounds from X-rays will improve in the next 10 years, so this will go down. So this paints a pretty dim picture of what is possible with shadows to measure these parameters, but let me end on a positive note. So going into the details, we find that the A01 parameter is actually, which is, by the way, is related to the RR component of the metric, is strongly dependent on the shadow size. And the W01 parameter, which is related to the TT and T phi component, is strongly dependent on the shape. What this means is if we measure these two parameters simultaneously, the bounds do not change much. So here I show you a simultaneous measurement with future data of A01 and W01. And you can see that the bounds do not change too much. This is actually very nice because, last minute?
Yeah.
Okay, perfect. So this is very nice because we don't know all the bounds that I showed here are obtained assuming only one non-zero parameter. And it is quite possible that when we do simultaneous parameters, the techniques, they will get worse and they might get significantly worse, making shadow measurements comparable to the other techniques. That's one positive note. Another positive note, of course, is we can do robustness checks with different techniques and different sources. So it's to do these kind of things with shadows. So I'll end there. Thank you.
Thank you very much. Let's go through all the presentations because we're still kind of short on time, and maybe we'll have a round of quick discussion afterwards. So thank you very much. And I will ask Pedro Cunha to give the last talk of this session.
Hello, can you hear
Pedro?
me?
Yes, I think you must be in best time to give talk among all the speakers.
Well, so regarding my time zone, it's 8 p.m. in the evening. Regarding your question,
that's the best time among all the speakers, closest to the working hours. Okay, yes. Take it away, please.
Okay, so just a moment. So just set the timer. So hi everyone, it is a great pleasure to be here. So in this talk, I will discuss the main result of this recent letter that was written in collaboration with Karls Aveiro and published in PRL as an editor's suggestion. And by the end of this talk, I will discuss an argument which hopefully you might find both simple and elegant. And although I cannot discuss the full details of the paper in just 10 minutes, I will try to convey the main idea and concepts. With observations of gravitational waves by LIGO and the black hole shadow by the Event Horizon Telescope, we now have a window into the strong gravity regime close to black holes. The observation signatures of both the gravitational wave ring down and the black hole shadow are strongly connected with a special class of null orbits that are called light rings. Light rings are specially closed circular null geodesics. In spherical symmetry, the clustering of light ring orbits forms the more familiar concept of a photon sphere. Light rings are known to exist in multiple spacetimes, such as Schwarzschild and Kerr, and the analysis of specific black hole solutions in the literature has built an expectation in the community that all black holes must be surrounded by a light ring orbit. However, this expectation is not generally based on a solid foundation. This leads to the natural question: does an equilibrium black hole always possess a light ring orbit? Although it is certainly plausible, it is also not trivial to give a generic answer. For example, how can we be certain that a light ring will exist around a black hole if we consider, say, a black hole that has no clearly defined equatorial plane? Nevertheless, it is important to state that a few results do exist in specific setups, assuming, for example, spherical symmetry. And in contrast, the result I'm going to discuss aims to be more general. So in this talk, we shall assume a very generic equilibrium black hole spacetime in 4 dimensions. The spacetime is assumed to be stationary and axially symmetric, which is reasonable in an equilibrium state. The horizon is also assumed to be a non-extremal Killing horizon with a spherical topology. We critically assume that the spacetime is asymptotically flat. We require continuous second-order derivatives, at least. And finally, we assume that the spacetime satisfies causality, which is fairly standard, and also circularity. Now, due to these Killing symmetries, we can then restrict the analysis to a spatial 2-dimensional space, which can be parameterized by an orthogonal spherical-like coordinates r theta. Then we can make some gauge choices. We can make the coordinates r theta reduce to spherical coordinates at asymptotic infinity, and we can fix the horizon at a constant radial coordinate. Having discussed the underlying spacetime assumptions, we can now make a few comments about the null geodesic motion. Due to the Killing symmetries, the Hamiltonian can naturally be used to construct a potential H. And importantly, a vanishing gradient of H is both the necessary and sufficient condition to determine the location of a light ring. And to simplify the discussion, I will ignore the fact that there are usually 2 potentials for H, each for a different rotation direction. I shall consider only the positive one. But now let's make a brief detour in our discussion. Let's assume for the moment that the scalar potential H now defines the height of different points on a hill. And the equipotential lines near the top of the hill will have a profile similar to the one in the left image here. Imagine now that you take a walk around the hill along the closed red path in the image. The gradient of your function H will always be pointing inwards, and it is simple to conclude that a maximum exists inside. But let's try to find a rule that expresses this intuition in a more concrete way. You can see here how the vector direction has changed with respect to the initial position A by looking at the angle indicator, which is the small circle next to the drawing. Importantly, as the person moves in the positive sense, the vector also rotates in the positive direction, as displayed by this green angle here. After returning to the starting point, the direction of the gradient vector is again the same. However, if you look at the integrated angle, it does not vanish. The vector has made one full turn in the positive direction. And this number does not depend on the exact path around the hill, as long as the hilltop is contained within the path. So we can then write our first rule, that a maximum or a minimum for that matter leads to one positive full rotation of the gradient vector. So now next we can take a more challenging setup, two small hills connected by a saddle point. Now, when walking in the positive direction of a path around the saddle point, the gradient vector is rotated in the negative direction. This is displayed in the angle indicator as a negative blue angle. And after returning to the initial position, the vector has made a complete rotation in the negative sense. So this is our second rule, which applies when the path contains a saddle point inside. So then what happens when we choose a path that includes both a maximum and a saddle point? As we start moving, the angle indicator starts showing a negative blue angle. However, at some point, the angle indicator can invert its direction. And in the end, after returning to the initial point, the integrated angle vanishes. So the conclusion is that the number of turns follows an additive property. The final number of rotations will simply be the sum of contributions of the stationary points inside the path. To apply this to our original problem, we first consider a two-dimensional plane that can be parameterized, say, by cylindrical-like coordinates rho z, with the black hole on the coordinate center. We then start defining our path. We can first choose a section with a constant radial coordinate close to the horizon, which can then be continued by joining two sections with a constant theta close to the rotating z-axis. And then we can close the contour with a section that has a constant radial coordinate at a large radius. Then we can modify the path and make it approach both the horizon, the axis, and spatial infinity. And it is under this limit that virtually any point outside the horizon can be contained inside the path. Now we can focus on the physical conditions. The condition for a finite Ricci scalar close to the horizon makes the gradient have a positive radial component. And in a similar way, a finite Ricci scalar close to the rotation axis fixes the gradient orientation in the direction of the axis. And finally, at the asymptotic infinity, the gradient must have a negative radial component. So now let's find out how the vector field rotates when we circulate the path in the positive sense. And you might find the angle indicator in the bottom right to be helpful for this. You can see right away that the vector starts rotating in the negative sense. However, the integrated angle does not need to have a monotonic behavior, and it can invert directions at some points, such as here, for example. But when all is said and done, after returning to the initial point, the gradient vector has described a complete negative rotation. So this means that there exists at least one saddle point of the potential inside the path. And by construction, this means there exists at least one light ring orbit outside the horizon. So this is the basic idea behind the argument and also the conclusion. Notice that we made no assumptions whatsoever for the matter content or the underlying gravity model. And this approach also shows how asymptotic flatness is a key boundary condition. So I will end with the following question. With other asymptotic behavior, can we construct black holes that possess no light ring orbits? Thank you.
Thank you, Pedro. I think that was very nice with all these geometric intuitions. First, let me clap. And now I think, according to the time, we have like exactly zero time for questions, but we caught up because before we had negative time for questions, which you admit is even worse. So let me ask our helpers if we can stay and chat a little bit, ask a couple of questions, or will this breakout room collapse?
That should be fine. It's not going to collapse, at least for a few minutes, or at least for a while. Okay. So yeah, you guys can have a discussion.
Okay. So we have formally we have a break now, a coffee break, but let's use some of it for a chat about any of the talks actually. So are there comments, questions that you would like to ask to the speakers? So there was quite a lively discussion.
I'll ask a question.
Please.
The first couple of talks were about naked singularities, and I just was asking how you get those naked singularities. Are they assuming that are the authors assuming that they're primordial, or?
So maybe one of the speakers would like to take that. Unless they went to sleep, which is.
Can you repeat the question?
So the first two talks, including yours, I believe, were effectively about naked singularities, the effects of naked singularities on photon light rates and so on. And I just wondered how you thought we would get these naked singularities. Is there, are you just assuming they exist and seeing what happens, or? It's because there's no obvious way to go from our physics to a naked singularity, unless you just assume they're there primordially, which is interesting. But
yeah, so I could share you two papers on the formation of naked singularities, which originates from the collapse of inhomogeneous cloud and results into formation of one kind of naked singularity. If you consider the Oppenheimer-Snyder collapse, so that resulted into the formation of a black hole, which was a idealistic, which considered idealistic conditions. But in this particular pairs of paper, they have considered a bit more generalized system, that it is not necessary that the collapse is going to be homogeneous every time. So they have considered inhomogeneous collapse, and the result was the formation of naked singularity. So I'll be sending you that two papers in this Slack. If you wish, you can go through them.
So I think it's also worth to comment that it's a common situation for these exotic objects. I believe that they wouldn't have an astrophysical channel of formation, like how to get a boson star, right? You typically say, well, what if there is a boson star and there is some astrophysical channel of formation of this that we just don't know and don't understand?
Yeah, like if they are satisfying the properties that we receive in the form of observations, so we can suggest that they exist, something like that.
Okay, so I would like to ask Prashant, you were raising hand for a while.
Yeah, hi. Pedro, that was really nice talk. I was wondering about your condition where you, this grad H that you showed, which you said was corresponded to the photon sphere. This is not, it looks like the expansion of the null congruence. So I would think that would probably, naively, I would think that corresponds to the event horizon. So is there an easy way for me to understand why this is the photon sphere? Or
sorry, is the question for whom? Is it for me?
Yes, yeah.
Okay, sorry. So can you, I'm sorry, can you repeat the question again?
Right. So you showed this condition grad H equal to 0, which told you where the location of the light ring was. I was just wondering why it corresponds to the light ring and not the photon sphere, not the horizon, because it looks like a vanishing null expansion. So.
Well, it's a very good question. What I can say, the conditions are different. So in that condition that the gradient of the potential is 0, essentially is saying that the null geodesic is tangent at each point along the killing symmetries of the spacetime. So in this case is stationary and axially symmetric, and that does not coincide necessarily with the event horizon. So it's a different condition.
Right, that makes sense. Thanks.
So I want to keep some chronology. I think Zach, you're the next one to ask question.
Okay, great. Yeah, thanks so much. These were all really interesting. I have a question for Pedro. I may have missed this in the conclusion, but so is the idea that we can use this gradient of H approach, is the idea that we can use it to make generalizations about the existence of light rings in arbitrary spacetimes?
Yes, so the idea is to find a general argument, in this case a geometrical one, why a generic equilibrium black hole must have one of these orbits. Of course, you can apply the method, so this integration contour, which I've not made very explicit in terms of mathematic formulas, just to keep it more friendly for this presentation, that you can write it down as an integral and compute it explicitly for a specific spacetime and arrive at the same conclusion that you must have a saddle point of the potential inside the contour. If the contour essentially is taken under that limit, that essentially covers almost all of the spacetime outside the horizon. But the goal of this result is to be applied in a very generic scenario, just to put on a more solid footing the kind of naive idea that all black holes must have one of these orbits. And what I try to show is that indeed that should be the case, at least under these assumptions. But there could be room for situations where this is not true. If you play with the boundary conditions, namely asymptotic flatness, it might not hold anymore.
Thank you. That makes sense.
Okay, thank you for your question.
Any more questions from the audience, from the participants? Oh, I see Boris.
Yeah, hello. This is sort of an open question to most of the speakers. That with the EHT and the ngEHT, when we look at black holes, we don't actually see the shadow, we see the thin rings of emission around them. And the two parts are the metric that you put in, or the gravity theory, and the actual effect of that metric on the accretion flow and the jet. And it was like, I've seen very little work to show how these how the flow changes with all these spacetimes, and whether you have some different MHD effects that can cause things that look like rings but aren't the shadow. So, have any of you seen what the effects of all these metrics are on the astrophysics?
So anybody would like to address this? I had a little problem in hearing the last part of your question, Boris. I don't know if others heard it well.
I can make a comment. So yes, I've been looking at exactly that thing. As you would know, GR MHD simulations are difficult to do even within GR, and outside GR it's even more difficult. But one of the things I've tried is to see how the how a disk evolves with the background given by this Johansen metric, which many of us have heard of, and it's not it is outside completely. It's not very strange. It also has a Carter constant, for example. So it has, let's say, the sort of symmetries that we expect, that we associate with the Kerr metric. And there I found nothing extraordinary. Everything evolves along similar lines as it does in GR, but the study is not finished yet.
So is this a GRMHD simulation in the Johansen metric?
I didn't hear that, sorry.
Is this a GRMHD simulation?
Yes, yeah.
Okay, that sounds incredibly interesting. I'd love to see that.
Yeah, I hope we have the result out soon.
Yeah, that sounds good. I know it's actually effort at least a couple of places to do some kind of GRMHD in non-Kerr spacetimes. So all of that is really interesting. And I think a big question would be, well, wouldn't GRMHD actually be indifferent to the background metric, and how much in these actual observables is the signature of the space-time? So I think we should give it at least 5 minutes before the plenary session. So let's finish with that. But of course, the Slack channels are open for further discussion. So thanks everyone so much for these really nice talks and some good discussion. Thank you, Mina and Paul, for helping with the organization of that. And well, see you around at this meeting further on.
And thank you, Maciek, for moderating.
Thank you. Oh yeah, let's clap hands for everybody. Good, thanks.